So this was the cosecant graph extended. So what we did here with this dashed portion, the dashed portion is actually sine. So we drew the sine graph, and then the zeros of the sine graph, which happen at 0, pi, 2 pi, 3 pi, negative pi, any multiple of pi. Those became the vertical asymptotes of the cosecant graph. Then from there, we took the shape of the sine graph and we flipped it in a way so that if you had a curve that was facing downwards, that became an upwards facing parabola under the cosecant graph. And similarly, if we had a curve that was facing upwards, we would take that, flip it over, and get a parabola that's facing downwards. And so the trick here was really just knowing what the sine graph looks like, and then based on that, drawing cosecant. So we're going to use that same idea by considering the reference graph to be for sine of x and worry about graphing that and using it to graph for cosecant x. Okay. Let me just try to fix the focus a little. Okay, I think that's a bit better. So we're going to consider the reference graph. And that is y is equal to 4 sine of x. Right, so when if we were to graph that first step, we don't need to have a step 0 first of all, because we don't have a horizontal translation, right? There's no phase shift. So we can jump straight to step number 1. And step number 1 is finding the period. The period is going to be 2 pi divided by b. B is the coefficient of x. So this should be 1. That means that the period is going to be 2 pi. Then the next step when we graph sine is to look for the step size. The step size is always given by the period divided by 4. So this becomes a 2 pi divided by 4, which is a pi over 2. Once we have the step size, we can compute the important x values. And again, what's nice about this is we don't have a phase shift, so we don't have to worry about first finding theta and then x. We can straight find the x values. So the first one is going to be 0 times the step size, so pi over 2, which is going to give us 0. The next one will be 1 times the step size, so pi over 2. Then 2 times the step size, which is going to be pi, right, because these 2's are going to cancel. The next one will be 3 times the step size. So we can treat this as being a 3 over 1. And if we do that, then we can multiply numerators together to get 3 pi and denominators together to get 2. And then the last x value is 4 times our step size of pi over 2, which is going to give us a 2 pi, because again, you can treat this as 4 over 1, multiply across and get a 4 pi over 2, but 4 over 2 reduces down to a 2. So we get 2 pi. All right, so remember, this is for sine of x. I'll go ahead and then on this table of points down here, create a new row that is for 4 sine of x and transfer over the x value. So that would be 0, pi over 2, pi, 3 pi over 2, and 2 pi. We're going to take those and plug them into the reference equation. So 4 times sine of 0, this is what we would get when we plug in the first x value, 4 times sine of 0. Sine of 0 is 0, so we're just going to get 0 in this case, right? So the first point is x is equal to 0 and y is equal to 0. So that's the point passing through the origin. Then the next one, and I'll go ahead and extend these as well, that way we can separate the work. Then we're going to plug in the pi over 2. So this becomes 4 times sine of pi over 2. Sine of pi over 2 is 1. So we get 4 times 1, which is just 4. So that means that we need to plot the point pi over 2 comma 4. And up to this point, I haven't really labeled any of the x tick marks, so let's do that first. This is going to be pi over 2, pi, 3 pi over 2, and 2 pi. And so we need to be able to cover a y value of 4, so I need to make sure that 4 is on here. What I'll do is I'll label this as a 2 and this as a 4. And then this would be negative 2. This is negative 4. Okay, so at pi over 2, we reach 4. Now repeat the process with pi. And this is going to be 4 times sine of pi. Sine of pi is 0, so 4 times 0 will give us 0. That means that we're plotting the point pi, comma, 0, which is this here. Next is 4 times sine of 3 pi over 2. Sine of 3 pi over 2 is a negative 1, so this is a 4 times negative 1, which is going to give us negative 4. And so then we've got 3 pi over 2, comma, negative 4. That would be, oh, and I think I have to be careful here. I need to label these the same unit apart, the same units for each tick mark as I did in the positive y direction. So this should be the negative 2 and this should be the negative 4. And so 3 pi over 2 comma negative 4 would be that point. And finally we have 2 pi. So 4 times sine of 2 pi means we have 4 times 0. And 4 times 0 is just 0. So we have the point 2 pi comma 0, which would be here. So what this tells us then is that our reference graph is going to look like this. Right, but remember, we the actual goal is for cosecant x. So what we're going to do now is find the zeros of the reference graph, the one that involves sine. And the zeros happen at x is equal to 0, at x is equal to pi, right? That's when we also have a y of 0. And when x is equal to 2 pi, that's also when we have a 0. We can also read them here from the graph. The zeros correspond to where the graph touches the x-axis. So that happens here at this point, and at this point. So at those 3 different places, we're going to have asymptotes. We're going to have asymptotes. So let's go ahead and draw it. This will be the asymptotes, and then maybe okay, just to be very precise here, I'm gonna draw these dotted because these aren't the actual graph, right? These are just lines, vertical lines that are gonna attract the shape of the graph. But solid line usually means that there is a point on that line that satisfies the equation. And in this case, that's not true. These are just a vertical asymptotes. So from there, we can use the reference to help us draw cosecant. In this part between 0 and pi, we see the shape of sine facing downward. So that means that in that little piece, in that interval, we're going to have a parabola that faces upward. And it actually is going to pass, or is going to touch the point pi over 2 comma 4. This should also be pi over, this should also be 4 for cosecant. Now, between pi and 2 pi, we have the shape of the reference graph facing up. So that means that at this point, we're going to have a parabola facing down with the vertex at 3 pi over 2 comma negative 4. So this would be negative 4 as well. And so at the end, what matters as the final part of the graph are just these parabolas that we're reading here. Everything else is just a guide or a reference to help us draw those parabolas. So any questions here with how to graph the 4 cosecant x? And what I'm going to do is I'm going to compare that onto decimals. We want to make sure that we have the correct answer. So I'll be using the Desmos graphing calculator, which is a free online graphing calculator. Okay, so I'll go ahead and share the whole thing. All right, so we had to graph 4 cosecant of x. And I'm going to restrict the window so that we see just like what we have. So maybe I'll go from like negative 0.1 to a maximum x value of 2 pi. And the step size was a pi over 2. For the y-axis, I think the maximum value that we had was, this would be 6, 8, 10. So I'll go from negative 10 to 10. We used units, increments of 2. Now when we compare, I'm also going to try to, before we compare, I'm going to draw the asymptote. So we had 3 asymptotes that we drew. One was a vertical asymptote through x is equal to 0. So remember, when we are given the equation of a vertical line, we have to write x equals and then the point through which it passes. Okay, so it passes through 0. This one is passing through pi, so this would be x is equal to pi. And then the next one would be x is equal to 2 pi. And which you can hardly see because we restricted the window a little there, but that's okay. But between 0 and pi, those 2 asymptotes, we see an upward facing parabola. If we look at where the vertex is over here on Desmos, we see that it happens at pi over 2 comma 4, which is precisely where we have our vertex as well. And then the between pi and 2 pi, we have a downward facing parabola with the vertex at 3 pi over 2 negative 4, which is the same exact thing that we have here. So our answer is correct. And notice they don't have the reference graph, they don't have the sign graph because that's not part of the answer. That's just something that we drew to help us get to the final graph. Any questions there? Okay. Let's consider the next example, which is on page, I'm looking at page 14 now. Now this one we have something that looks a bit more complicated. We have y equals negative 1 minus 3 secant of pi x over 2 plus 3 pi over 4. So again, we're going to consider the reference graph, and I'll abbreviate this REF graph. And the reference graph is going to be y equals negative 1 minus 3. Now the reciprocal of secant is cosine, so it's going to be cosine pi x over 2 plus 3 pi over 4. That's what we want to graph. So now based on that equation, because this does have a phase shift, meaning a horizontal shift, we're going to take care of that first using a step 0. And we're going to write it as -1 minus 3 cosine. We have to pull out the coefficient of x. Now this might look a little intimidating because the x is not by itself. There's like a pi being multiplied with it and then dividing by 2. But remember that, in fact, I think I still have this work that I did for my Wednesday section last week. But this pi x over 2, we can write it as a pi over 2 times x over 1, right? Because we would multiply numerators together and denominators together, and it would give us this. But the benefit in writing it this way is that we can see then x over 1 is the same thing as just x. So this is really just pi over 2 times x, which we could write as pi over 2x. And so that lets us see that the coefficient of x is this pi over 2. Okay, so we're going to be factoring out a pi over 2, which is going to leave us with an x plus. Now, in order to determine what is the second term that gets left over here, we need to remember that when we're factoring, we're essentially dividing by whatever number we're pulling out from the parentheses. So since I'm pulling out a pi over 2, that means divide the first term by pi over 2 and divide the second term by pi over 2. Okay, so doing some side work, we have 3 pi over 4 divided by pi over 2. That's the same thing as 3 pi over 4 times the reciprocal, 2 over pi. The pi's are going to cancel, and then we can multiply across numerators to get 6, multiply across denominators to get 4, and then the 6 over 4 reduces down to a 3 over 2. So what we get here then is a 3 over 2. Questions at that point? You can always verify whether you've factored correctly by redistributing this back in and seeing if you get this original expression. All right, so then what we do is we're going to replace the phase shift with theta. So we're just going to set let theta be x plus 3 over 2. And then that means that we're going to get a new, more simplified equation. It's going to be y equals -1 minus 3 times cosine of pi over 2 times theta. Because again, what we did here was we took this x plus 3 over 2 and replaced it with theta. Okay, so now we can find the period. The period is going to be 2 pi divided by b. And b in this case is this pi over 2. So that means we have a 2 pi times, remember that dividing is the same thing as multiplying by reciprocal. So the reciprocal of pi over 2 is 2 over pi. And then in order for us to be able to multiply that, I'm going to write the 2 pi as a 2 pi over 1. And that'll give us, well, the pi's are going to cancel. That's just going to give us a 2 times 2 is 4 over 1, which is just 4. Okay, so the period is 4. Then we take a look at the step size. The step size is the period divided by 4. So that's a 4 over 4, which is 1. Now we want to find the important x values, but to do so we first need to find the values without the shift, which are the theta values. Okay, so without shift, we're going to have theta 0 is equal to 0 times the step size, which is just going to be 0. And theta 1 is going to be 1 times the step size, which is 1. Then 2 times the step size, that's just 2. 3 times the step size, that's just 3. And 4 times the step size, which is going to be 4. That's without shift. Now with the shift, we have to go back to this equation and solve for x. Okay, so if we solve for x, we're going to get that, and I'll write it here because I'm not going to have enough room to write it up here. We're going to get that x is equal to a theta minus 3 over 2, right? Because we're subtracting a 3 over 2 from both sides of the equation. So now with the shift, we would have x0 is going to be theta 0 minus 3 over 2. I'm just rewriting this equation down, that relationship. And now we can replace what theta 0 is. It's the 0. We're going to replace it into here. And we're going to get 0 minus 3 over 2, which is just going to be negative 3 over 2. And repeat with the next value. x1 is going to be theta 1 minus 3 over 2. And theta 1 is a 1. So we get 1 minus 3 over 2. I'm going to write the 1 as a 2 over 2 so we have the same denominator. Okay, so 2 minus 3 will give me a negative 1, and then denominator is 2. All right, the next one, x2 will be theta 2 minus 3 over 2. That means that we have a 2 minus 3 over 2. And that becomes 4 over 2 minus 3 over 2 for the same reason. We're trying to have the same denominator. So then 4 minus 3 will give us 1 over 2. Next one, theta 3 minus 3 over 2. That's a 3 minus 3 over 2, which becomes 6 over 2 minus 3 over 2. Again, I'm just writing the 3 over a common denominator of 2. And that's a 3 over 2. And then our final x value would be theta 4 minus 3 over 2, which is going to be a 4 minus 3 over 2. And that's an 8 over 2 minus 3 over 2, which gives us a 5 over 2. So that's with shift. I'm going to transfer those values over to the table of points, these important x values. So we have negative 3 over 2 for x0, then negative 1/2 for x1, x2 is 1/2, x3 is 3/2, and x4 is 5/2. I'm also going to create a separate row here for the reference graph. And I'll start writing the reference in red just because it's not what we're really looking to graph. So just so that it's a different color from the actual graph. And that's something I didn't do for the previous page, but I'll start doing here. Okay. And then because this is slightly a bit longer, instead of doing it by hand, I'm going to use the calculator. I'm also going to write this a little differently too so that it's easier to punch in. I'm going to write this as a pi over 2 times x. Okay, we said the reason why we're able to do that is this, because pi x over 2 is the same thing as pi over 2 times x over 1, which is the same thing as pi over 2 times x. So that's what I'm doing. All right. So for the reference values, we've got a negative 1 minus 3 times cosine of pi over 2. So I'm going to go ahead and enclose the pi over 2 in parentheses to make sure that that gets computed as one fraction. And then we're multiplying it times the first x, which is negative 3 over 2. And again, I'll enclose that in parentheses to make sure that gets computed as one fraction. And then we have plus a 3 pi over 4. I'm using parentheses again because I want to enclose the fraction, make sure that that gets computed by itself. So then, according to the calculator, this would be a negative 2. Right. The next x value is a negative 1/2. So what I'll do here is I'll change this, the rest of, oh, and actually I have to be careful because there should have been a 3 here, huh? So I don't have the 3, I'm missing that 3. I'm gonna have to go back. Yeah, I'm gonna have to go back and insert the 3 there and recalculate. Okay, so let me just double check. We've got negative 1 minus 3 times cosine of pi over 2, that's one fraction, times the first x value of negative 3 over 2, so that's this open parenthesis negative 3 over 2 close parenthesis to close the fraction. Then we have plus a 3 pi over 4, close the fraction of the 3 pi over 4, and then close the cosine. Okay, so now we get negative 4. Right, so be careful there. Okay. So I'm going to bring back that same computation, but I'm going to replace, because we have an x of negative 1/2, I'm going to replace this second fraction that's being multiplied with pi over 2 with a negative 1 over 2. And then everything else remains the same. When we get a y value of negative 1, the next x value is 1/2. So again, I'll bring that back, that computation, and in this case, all I have to do is remove the negative from the 1/2, and we get a value of 2. Then the next y value is 3 over 2. So I'm going to replace that 1/2 by 3/2, and I get negative 1. And then the last one is 5 over 2. So I'm going to remove that 3, replace it with 5. And so we get negative 4. So any questions about the values that we're getting down here for cosine? We're doing okay? Great. So let's see. I'll label the x and y axis first, and then we'll go and we'll draw the reference graph. The smallest x value I need is a negative 3 over 2, and the largest is a 5 over 2. So let's see, if I make this like negative 1/2, this would be negative 1, this would be negative 3 over 2, and that would fit the smallest value. Using the same unit distance, the distance between each tick mark, we're going to have this being 1/2, then 1, then 3/2, then 2, then 5/2, and that's as far as we need to go, right? So that should be good enough for our needs. And we need the lowest y value we have is a negative 4. The largest is a 2. So I'll make this a negative 2, and this a negative 4, and this a 2. All right. So first point on the reference graph is negative 3 over 2 comma negative 4. This is negative 3 over 2 comma negative 4 is down here. Then we have negative 1/2 comma negative 1. So negative 1/2 comma negative 1, that would be here. Then 1/2 comma 2, 1/2 comma 2 would be here. 3/2 comma -1. So here's 3/2 comma -1. It's there. And then the final one is 5/2 comma -4. So that would be here. All right. So the reference graph, remember this is cosine. Cosine is curvy. It's going to be passing through these points. And if we think about what exactly happened to the cosine graph, well, if we just take a look at the equation, we see that it needs to have an amplitude of 3, right? Because there's a 3 in front of the cosine. Moreover, it's going to be it's going to be reflected, excuse me. It's going to be reflected. So instead of starting, usually cosine, and I'll draw it here, and usually cosine begins up in the positive y direction and then goes down and then back up, right? So usually we would have had like, oh, it begins at 3. Because of this negative, that means it's going to be reflected. That means it's going to be, it's going to start at -3 and go like this. And on top of that, we have a downshift of -1. So this is going to get pushed down to -4. Okay, so it's going to look something like that. Okay, something like that. And it has been shifted. It has a phase shift. Because we have plus some number, that means it's actually going to be shifted to the left. So we're going to end up with something that starts behind the y-axis, right? So precisely what we see here, something like that. What that means is that where we normally would have zeros for the cosine graph, that has also been shifted down by 1, right? So if this wouldn't have been shifted down by 1, the zeros would be at this position, right here. So that means that there is where we're going to see our vertical asymptotes. And between -3/2 and -1/2, we have half of this curve that is facing up. That means that we're going to have half a parabola facing down. Then between -1/2 and 3/2, we have this parabola, this curve that is facing down. That means that we're going to have a parabola facing up. And finally, between 3/2 and 5/2, we have half of this curve facing up. That means that we're going to want half a parabola facing down. And they are going to have vertices 1/2 comma 2, -3/2 comma -4, and 5/2 comma -4. The questions there? Let me share the full screen so that we can see Desmos as well. So comparing with what Desmos gives us, we've got -1 minus 3 secant of pi times x divided by 2 plus the 3 pi over 4. And then I'm going to change, I'm going to restrict the window between -3/2 for the lowest x, and then the highest x would be 5/2 with a step size of 1. And then for our y-axis, I think the largest that we drew was like a positive 4. And the smallest that we have is a, let's see, like a negative 8. Okay. Right, so let's look at that comparison. We have, I'm going to zoom out just a little bit. We have a vertex at negative 1.5 comma negative 4. Negative 1.5 is the same thing as this negative 3 over 2. Oh, sorry, I might put away all this. So it's the same as this negative 3 over 2, because 3 divided by 2 is 1.5. So negative 1.5 comma 4 is correct there. And the reason why you can see the full downward facing parabola is because I zoomed out of the window. So a similar thing would happen here. If I were to like zoom out of the window or consider the additional points, I would see the graph continue to create the full downward parabola. Okay. But essentially what we're seeing is this portion of the graph. Then we have an upward facing parabola with the vertex at 0.5 comma 2 mondecimals. In our paper, we have 1/2 comma 2, which is exactly the same thing. And then the last parabola, we have 2.5 comma negative 4. We have a vertex at 5 over 2 comma negative 4. But remember, 5 over 2 is the same thing as 2.5. And again, we only drew half of the parabola because we restricted to one cycle, so we're not seeing the full extension of this. But if we were to consider more x values that are greater than 5 over 2, then we would see the rest of this downward facing parabola. All right. Now, we also said that we had 2 asymptotes involved in this one cycle. One of the asymptotes was passing through this x equals negative 1/2. So we've got x equals negative 1/2. That's one. And then the other one was passing through the 3 over 2. And that's the second. All right. So that means that our work on our paper is correct. And I'll highlight just the parabola portions because those make up the actual solution of the, or the real graph of this equation here. Any questions? Sorry, apologies. One more thing. I forgot to fill out this part of our graph on page 14. So let me just focus on the document here. All right. So at negative 3 over 2, which is here, we have the vertex of negative 4. So that is the same as with the reference graph. Then at negative 1/2, that's where we have our asymptote. At 1/2, we have vertex of 2, so this is the same as reference. Then at 3 over 2, we had our asymptote. And finally, at 5 over 2, we had a y value of negative 4. All right. Questions first?
Can I see how you inputted the formula in the calculator?
Yeah, definitely. So
I'm not coming up with the correct answer.
okay, yeah, no problem. So what I did, let me take this out of the picture. What I did is I did negative 1. So the negative symbol, then 1. And then minus a 3 times cosine. And what I did here was I enclosed the pi over 2 in parentheses to make sure that that gets computed as one fraction by itself. And then we're going to multiply with the first x value, which is a negative 3 over 2. So multiply with negative 3 over 2. And this is closing the second fraction. Then we have plus and I'm going to start using parenthesis, open parenthesis again here because I want to write the 3 pi over 2 as one group, one fraction that should be computed, independently of anything else that's going around it. And so when we do that, we get this first one of -4. And then so that I don't have to re-enter the same thing over like the -1 minus 3 cosine, all of the values that stay the same, so I don't have to re-enter that. On my calculator, there is a setting called entry. And what that does is, well, first of all, in order to get to it, that means I need to press the second and then the enter key because it's in blue. So second and then enter. And what that does is, oops, sorry, let me try that again. What that does is it brings back the last computation that I did, which was this one here with the -3/2. But I can now go in and modify it. So I want to modify it so that instead of having an x of -3/2, I have an x of -1/2. So I changed that 3 to a 1. Okay. And everything else stays the same. -1 minus 3 cosine, and then pi over 2 in parentheses to make sure that that gets grouped together, multiplied with a -1/2, so that's also in parentheses to make sure it gets grouped together. And then plus 3 pi over 4, that needs to be in parentheses so that it gets grouped together. And then one final parenthesis to close the cosine. And then we get the -1.
And that's in radians, right? Not degrees?
Correct, yeah, and that should be in radians.
Yeah, I have it inputted exactly that way you have it, but I'm not coming up with anything past the -4.
Did you double check the parentheses here that everything is closed, open and closed in the correct spot?
Yes, multiple times.
Yeah, okay. What about this one here? Did you include this last parenthesis? So it should be, let's see, in the end, we're going to have 1, 2, 3, 4, 5, 6, 7, 8 parentheses. We have all 8 of them.
Yeah, I just counted 8.
8, okay. That's interesting. And it's for sure in radians, right?
Yeah, I don't know why I don't know what I'm doing wrong, but every time I've been doing this, it's come out right. So I'm surprised.
What value is it giving you?
Once I enter -1/2, it gets me 3.99.
Huh. That's interesting. What about the 1/2? Let's
I get -3.12.
okay.
I'll figure it out. I was just double checking to make sure I wanted to see it once more, but I'll figure it out.
Yes, apologies that that I don't have a better answer for it. My guess would be the parentheses, but if that's exactly the same, I'm not too sure what could be the issue. Yeah, sorry. All right, so we're going to continue with page 11. And again, we're going a little out of order, but that's because I want to start with cotangent because cotangent is actually a little bit easier to work with than tangent. It looks similar to the process that we've already been doing, and tangent diverges a little bit. So let's go to cotangent first. Okay. And I'm going to bring up the graph of cotangent so that we can remember what it looked like.
I figured it out. I did 3 pi over 2 instead of 3 pi over 4.
Ah, okay, good. I see. Because of the original one had like 3 pi over 4 before we factored. Sorry, the factored one had a 3 over 2, right? I think that's maybe where the mix-up.
Yeah, and I kept checking and it was wrong. I was like, wait, and then wait, let me check that number again. Oh yeah, there it is.
Yeah, okay, good. I'm glad it was that and not something else, because sometimes, it's the little things that once you look at it again, you're like, oh my goodness, I can't believe I spent so much time for that one thing. No, so I'm glad it was something that we could pick up. All right, so right now I'm sharing with you guys the cotangent graph, and actually if I go back one page, you can see one cycle. The cotangent graph, what was kind of different about it, but if we compare with sine and cosine, and now with secant and cosecant, is it doesn't complete one cycle in 2 pi radians. It actually completes it in pi radians, right, between 0 and pi. So that was one big difference. Another big difference is the fact that unlike sine and cosine, it doesn't oscillate. It has kind of like it's continuous between 0 and pi, meaning there are no breaks. But then after 0 or right at 0 and right at pi, that's where we see these vertical asymptotes. So the graph there breaks. And then if we were to zoom out of that window, we would see a repetition of that same curve between pi and 2 pi, between 2 pi and 3 pi, and similar in the negative x direction. And so that's the original cotangent graph without any modifications done to it. Now the graph that we have now is the 1/2 cotangent of negative 2x. And so to graph that, I also want to show you this page. It was page 13 that oh, I went over the wrong way. Oh. Okay. In this, it told us that the tangent graph is an odd function. So odd means that whenever you have a negative in the argument, that you can bring it out. And the same is true about cotangent. Whenever there is a negative in the argument, we can bring it out. And so that's going to be relevant to the problem that we're doing right now, because in this problem here, we have a negative 2 times x, which is part of the argument of cotangent. So because it's odd, we are able to bring it out. So I'm going to call that our part of our step 0. We're going to get y is equal to negative 1/2 cotangent of 2x, and then I'll give the reason why on the side. Because cotangent is odd. So that means that this negative, we can bring it all the way outside. And if we would have had a phase shift, this is also the step at which we would have taken care of that, but thankfully we don't have that phase shift. Then the next step, and this is the first time that we were doing it with cotangent, so this is something I want to pay special emphasis on. Normally, the period for sine, cosine, secant, cosecant is 2 pi over b, but for cotangent and tangent, the period is just pi over b. So that's in general just pi over b. Now the b in this problem is 2. Oops, wrong color. Is 2. Okay, so we're going to replace that with 2. That means that the period here is going to be pi over 2. Then the next step is the same as what we've been doing, is to find the step size. And the step size is the period divided by 4. So that means we have a pi over 2 divided by 4, which is the period over 2 times, remember division is the same as multiplying by reciprocals, so that's the same as times 1 over 4. So we get pi over 8. Then the next step is to find the important x values. Now, the x values in this case, the important x values will include asymptotes. Okay, so usually we have our first asymptote at 0. So we're going to get x0 is going to be 0 times the step size of pi over 8. So we get 0, and this is going to be an asymptote. Then x1 would be 1 times the step size, which is going to be pi over 8. This is an expectation, and even if you forget at this point, it's okay. Once you plug in this x value into the equation, you'll see that it'll give you undefined. So we'll know that that is an asymptote. Okay, so for now, we're just kind of expecting that to be an asymptote. And we have 2 times pi over 8, and that'll be a 2 pi over 8, which we can reduce down to a pi over 4. Next, we have a 3 times pi over 8, and that's going to be 3 pi over 8. The last one is a 4 times pi over 8, which is going to be 4 pi over 8, and reduces down to a pi over 2. Okay. So let's transfer our x values onto the table of points. We have 0, pi over 8, pi over 4, 3 pi over 8, and 3 pi over 2. I'm going to compute these directly by hand and with the aid of the unit circle. The reason being is that the calculator can sometimes be a little difficult to read when it's either an asymptote or a 0, because we have to compute it as 1 over 10. And so that can introduce some confusion there. So I think it's best that we just compute it by hand and then use the unit circle to help us out. Okay, so this is going to be 1/2 cotangent.
Professor? Wouldn't the last number in the table of points be pi over 2?
Yes, thank you. I don't know why I wrote 3 pi over 2. I think I don't know. Yeah, but you're absolutely right. It's pi over 2. Thank you. All right, so we've got a -2 times 0, and this is going to be 1/2 cotangent of 0. Okay, so then let's go back to our unit circle. So this is a unit circle that has already been pre-printed, not the one that we have on the lecture notes, but you can find the unit circle anywhere online. So this is one that I found online, and I'll also post up as a reference for you guys. But we're looking at cotangent of 0 radians. So here is 0. The point that's associated to that is 1, 0. So that means the x is 1, but the y is 0. Remember that cotangent of any angle is given as x over y. Right? That was one of the trig definitions that we learned. The second way to think about the trigonometric definitions was with these points on the unit circle. And it was for cotangent, it turned out to be x over y. So cotangent of 0 is going to be 1 over 0, which is undefined. So that means that here, this is undefined. And whenever we have something that is undefined, that means that we have an asymptote. So at x is equal to 0, we're going to have an asymptote. On this way. All right. Then we can repeat the process with the pi over 8. So we'll have a 1/2 cotangent of -2. times pi over 8. And then that would be a negative 2 pi over 8, but negative 2 pi over 8 is the same thing as a negative pi over 4. So this is 1/2 cotangent of negative pi over 4. Now, if you wish, you could look at negative pi over 4 on the unit circle, but since I think it's easier for us to deal with positive angles, I'm going to apply the fact that cotangent is an odd function to bring this negative from out to the outside of the expression. So this is the same thing as negative 1/2 cotangent of pi over 4. All right, so here's pi over 4. Cotangent of pi over 4 is going to be the same thing as x over y. So in this case, x is a radical 2 over 2, and y is also a radical 2 over 2. So that means that this is just 1, right? Because numerator and denominator are the same. So when that's the case, we have 1. That means that we have a negative 1/2 times 1, which is just a negative 1/2. All right. I'm going to continue coming up with these values, and then at the end we'll label the x tick marks and plot the points. Okay, so let's plug in the pi over 4. We have a 1/2 cotangent of negative 2 times pi over 4, which is going to be 1/2 cotangent. Negative 2 times pi over 4 is going to reduce down to a negative pi over 2. Again, I'm going to apply the fact that we can move the negative all the way outside the expression. So we get negative 1/2 cotangent pi over 2. Now, if we look at pi over 2, cotangent of pi over 2 is going to be x over y. So we've got 1 over 0, and that is going to give us, that's a 0 over 1. Right, x over y, 0 over 1. So that's a 0. I want to be careful there. It's x over y. The x is 0, the y is 1. So this becomes a 1/2 times 0, which is just going to be 0. All right. Next value is a 3 pi over 8. Again, 1/2 cotangent of negative 2 times 3 pi over 8. That becomes a 1/2 cotangent of negative 6 pi over 8. That reduces to a negative 3 pi over 4. Then we'll bring the negative to the front. So we've got negative 1/2 cotangent of 3 pi over 4. And then at 3 pi over 4, we've got an x of negative radical 2 over 2, negative radical 2 over 2, and then y is positive radical 2 over 2. So when we divide the x by the y, we're going to end up with just a negative 1. Okay. This is negative 1/2 times 1, which is going to be negative 1/2. All right, we have one last one. 1/2 cotangent of negative 2 times pi over 2. That becomes 1/2 cotangent of negative pi. We can bring the negative to the outside to get negative 1/2 cotangent of pi. At pi, we have an x of negative 1 and a y of 0. So we get undefined. Right? Negative 1 divided by 0 is undefined. So this is undefined, which means we have an asymptote. Okay. All right. So let's label the tick marks now. coming back to the x-axis, the smallest unit is pi over 8. So I'm going to go up in increments. In fact, our step size is like pi over 8. Okay, so I'm going to go up in the step size of pi over 8. This is 1 pi over 8. This would be 2 pi over 8, 3 pi over 8, 4 pi over 8. And I think that's as far as we would need to go, right? Because 4 pi over 8, that reduces down to a pi over 2. 3 pi over 8 doesn't reduce, so that we can just write it as it is. And then the 2 pi over 8 reduces to a pi over 4. Yeah, so it's literally just 1, 2, 3, 4, and then reduce whenever you are able to reduce. Okay. So what happens? Oh, and then I need to label the y's. The y's, we just need 1/2 and negative 1/2. So I'll make this my 1/2 and this my negative 1/2. Okay. So at 0 we have an asymptote. We already drew that. At pi over 8 we have negative 1/2. So that's this point. At pi over 4 we have 0. At 3 pi over 8 we have negative, oh, did I make a mistake here? I think I did. Let me be careful. 3 pi over 4, let's see, let me double check. So at 3 pi over 4 we had negative 1. At, I think the mistake might be at the pi over 8, because at the pi over 8 we got pi over 4, and that should have been 1. Oh, sorry, the mistake is here. This was negative 1, right? This one here was negative 1. Yeah, let me show you. Cotangent of 3 pi over 4 is negative, right? Is this negative radical 2 over 2 divided by radical 2 over 2, which gave us negative 1. And then when I transferred it over to here, I didn't write it as a negative 1. So that should have been negative 1, and then negative times negative becomes positive 1/2. So it says 3 pi over 8, positive 1/2. And then the last one is pi over 2 comma asymptote. So this is really just asymptote at pi over 2. Okay. Now, even though it seems like they're going in a straight line, we have to be very careful here because this is tangent. And tangent is curvy. It curves, passes through the 3 points, and then starts getting really close to the asymptotes when it has a chance. It'll look something like this. Gravity problem. I dropped the negative. Gravity problem. Okay. Questions with this problem number 8?
Excuse me, Professor.
Mm-hmm.
Sorry, this is kind of a stupid question. I think how do you know when to use the unit circle or when to just I guess do the problem with your calculator like we did the last 2 problems?
Yeah, I would say whenever you're dealing with tangent and cotangent, try to do it by hand. And here's the reason why. Like, we could still use the calculator. We could still use the calculator, but if I do like 1 over 2, so that's the 1/2. The cotangent, I would have to write it as a 1 over tan, right? So I would have to write 1 over tangent of negative 2 times, let's say, times 0, right? And this one is okay. It's going to tell us, hey, you're trying to divide by 0, so that one will be okay. We'll say, okay, that means that there's an asymptote. But then when we get to this pi over 4, I'm going to change it now. -2, oh, sorry, let me try that again. -2 times, I'm going to insert some parentheses around the pi over 4. So pi over 4. See, is that balanced? We've got open, close, open, and then open, and then open. This closes the fraction of pi over 4. This is going to close the tangent, and then I would need one more to close the 1 over tangent. That's going to give me a domain error, and so I might be tempted to think, oh, this means that there must be another asymptote here. But really what's happening is that because we're computing it as 1 over tangent, tangent of, let me go back, tangent of -2 times pi over 4 is tangent of negative pi over 2, which is the same thing as negative tangent of pi over 2. And if we compute what is tangent of pi over 2, that's where the error comes from. And if we look at, oh, sorry, go ahead.
Oh, no, I said, oh, okay.
Yeah. So, so I would say whenever you're dealing with tangent or cotangent, do it by hand rather than do it by hand if you end the unit circle rather than by the calculator.
Okay, thanks.
You guys have any other questions? Okay. We're going to do one more, but this problem, we're actually going to modify it a little bit. We're not going to worry about cases in which we have the phase shift for tangent or for cotangent. The textbook doesn't require these types of problems, so I won't require it either. Okay, so we're just going to have y equals, if I were to rewrite this, it would be y equals 3 plus 2 times tangent of x over 2. That's what we're going to be graphing. Okay, so we're going to start by finding the period, because thankfully there's no negative inside of the argument for us to bring out. So we can jump to straight to step 1, which is the period is pi divided by b. Now in this case, what is b? Anyone want to take a guess?
X over 2.
Very close. It's actually, it's just the 1 over 2, right? Thank you for, is it Lee that commented on chat? So thank you. It's 1/2. And the reason is because this can be written as 3 plus 2 times tangent of 1 over 2 times x, right? So the coefficient by itself is 1/2. So we get pi over 1/2. And then dividing is the same thing as multiplying by the reciprocal. So times 2 over 1, that's like pi times 2, which is going to be 2 pi. Okay, so just be careful to never include x as part of the period. Okay, only the coefficient, only the constant that's in front of the x. Right. The next step would be to find the step size. And the step size will be the period divided by 4. So the period is 2 pi divided by 4, which is going to be a pi over 2. Okay, and this is where it gets, oh, question, why did we cross out the pi over 8? We crossed it off because this is basically going to introduce a phase shift for the tangent. And since the textbook doesn't really give you problems where you have phase shifts for tangent, I'm not going to give you a problem like that either here or in the exam. So I'm not going to worry about the problem where you have a phase shift. I'm just going to worry about problems like this for tangent. Yeah. No problem. And step 3 is where this is now where it gets very different to what we've seen so far. Because usually what we do is now we want to look for the important x values. So now we do like 0 times the step size, 1 times the step size, so on and so forth. But in this case, for tangent, let me go back to showing you what tangent looks like. Tangent does not begin its continuous cycle at 0. It actually begins it at -π/2. So let me show you what that looks like by bringing the old the notes from 2 weeks ago. Right, so here is tangent. And as you can see, the first asymptote does not happen at 0, it happens at -π/2. And then from there, we see a continuous 1 cycle, and then we see the second asymptote at π/2. So when we're thinking about what are the important x values, we have to see where does the first asymptote happen. And if this were just tangent of x, then the first asymptote would happen at -π/2. Okay, so let's just write that down and try to think about how it's going to modify the work that we do. Okay, so the first asymptote happens at, okay, actually, let me write it this way. Let's say that we had theta instead of x. Okay, so the first asymptote for y is equal to tangent of theta happens at theta equals -π/2. Okay, that's when we have tan of -π/2 is undefined. So that's an asymptote. So now, if we compare that against what we have a 1/2 x instead of a theta. So that means that we would want the 1/2 x to be equal to -π/2 to get that undefined. Okay, so in our case, the first asymptote happens when tangent of 1/2 x is equal to undefined. So i.e. when 1/2 x is equal to -π/2. Okay. So you can think of these, and I'll color code this. You can think of this theta as standing in the place of this 1/2 x. Okay. When theta is -π/2, tangent of theta is undefined. So in our case, that means that we want the 1/2 x to be this -π/2. Is that okay? Do you guys have questions about that?
Why didn't we do the last one like this?
The last one wasn't like this for cotangent.
Hmm.
Yeah, good question. So the last one wasn't like this because the original cotangent graph actually has an asymptote at 0. So let me show you what I mean by that. Let's go back to this one. I'm just gonna have to rotate it. Okay, so this was cotangent. If we take a look at where the first asymptote for that one is at 0. So because it's at 0, I mean, technically, if we would have had, say, like 1/2 cotangent of 1/2 x, because the asymptote happens at 0, we would just want 1/2 x to be equal to 0, which would still give us x is equal to 0. So it would still have the first asymptote at the same place where the original cotangent graph has it. But for tan, that is not the case. For tan, it begins at a place other than 0, and so we have to be careful about how we find x, the first x value in that case.
Okay, okay, thanks.
All right. So that means that for the process, the first x value, x0, is going to be given by this equation. And that means multiply both sides by a 2 to isolate the x. These cancel out, and we end up with, and these are also going to cancel out. We're going to end up with negative pi. Then the first, the x1, the next point, we can find by taking the first asymptote, negative pi, and adding 1 times the step size to it. So 1 times pi over 2. And that's going to be a negative pi plus pi over 2, which is a negative pi over 2. The next one, again, we start at the first asymptote, negative pi, and then add 2 times the step size of pi over 2. This becomes a negative pi plus pi, which is equal to 0. And then the one after is negative pi plus 3 times pi over 2. And then that gives us a negative pi plus 3 pi over 2, which we could write as a negative 2 pi over 2 plus 3 pi over 2. And that gives us a pi over 2. And then the last one is, again, the first asymptote plus 4 times the step size. So that's negative pi plus 2 pi, which is going to be pi. All right, so just to stress this again, this only happens with tangent. With tangent, you're always going to have to get whatever is in the argument. So like, let's say that instead you had like 4x, for example, you would need to take the 4x and set it equal to this negative pi over 2. Okay, so I'm going to write a note here on the side that says, in general, the first asymptote is going to be given by setting theta, let's say that we're going to call this b, right? In general, we're going to have b times x is equal to negative pi over 2, which means that the first asymptote is always going to be negative pi over 2 divided by b. And that's what you have to remember for tangent. And then once you have that first asymptote, the next values you just find by doing the usual 1 times the step size, 2 times the step size, all the way down to 4 times the step size. But then you also have to add the first asymptote. Okay, so if you wanted to write a general formula for it, we could do xi, where I is representing this little subscript, would be this asymptote, which is x0, right? So it would be x0 plus this, the I again, the subscript I, times the step size. And so this is again in general, x1, x2, x3 are given by this. And that's the hardest part about tangent. It's this step. Once you have these points, you can bring them onto your table of points, negative pi over 2, 0, pi over 2, and pi. And you can plug them in. So again, because it's tangent, might be a good idea to do it. Well, for tangent, you can plug it into the calculator with a little bit more confidence because we have a key that's exactly tangent. For cotangent, that's where we have the issue. So let me backtrack on what I said earlier. You should use unit circle for cotangent. For everything else, the calculator is okay, including tangent. So I'll revise what I just said. Okay, so for here, it's okay to use calculator. So we've got 3 plus 2 times tangent of x over 2. So in this case, we've got a negative pi over 2 plus a pi over 8. Oops. Okay, so let me just make sure parentheses look okay. I've got negative pi over 2 for the first fraction. Close the parenthesis, and then plus pi over 8 for the second fraction, close the tangent. And so we're getting, okay, so let me say this. This to me looks a little bit suspicious because what was supposed to happen at this point? Do you guys remember? Oh, and then, okay, hold on, that's what I'm doing wrong. We said we were gonna eliminate this, right? We didn't care about this part. Let me backtrack. 3 plus 2 times tangent of negative pi over 2. Okay, that's better. We were expecting an asymptote. Okay, we said at this point, negative pi, that's where we were going to see our first asymptote. So this looks good. Okay. Now the next x value is this negative pi over 2. So we're going to clear that, bring it back, and then we're going to have a negative pi over 2 divided by 2. Okay, I have an error in my syntax. Let's see. Oh, I think I have a curly brace instead of, there we go. We have a 1. Okay, so this here is a 1. Then the next x value is a 0. So again, I'll bring back that computation and replace the negative pi over 2 with a 0. Oh, sorry. I get 3. The next one is a pi over 2. So I'm just going to eliminate the negative. And that gives us 5. And then the last one is just pi. Okay, that's domain error. This means that we have an asymptote. All right, so let's label our tick marks. I'll make this negative pi over 2, 0, pi over 2, and pi. At negative pi and pi, we have asymptote, so that means we have this here. Then I should have y labels for 1, 3, and 5. So we'll just go the usual 1, 2, 3, 4, and 5. Okay. So negative pi over 2 comma 1 would be this point. 0 comma 3 would be this point. And pi over 2 comma 5 would be here. So that means that we have a tangent graph that curves through those 3 points. and then opens close to the asymptotes. This is something like this. For page 12, we don't have to worry about horizontal translation. That's not going to be tested. So rather what we're seeing is y is equal to k plus a times tangent of bx, or y is equal to k plus a times cotangent of bx. Okay, so don't have to worry about this portion. So if we have that, we just have to remember that the period is always given by pi divided by b, where b is the coefficient of x. So it's this one. Right. And then the vertical translation is the same exact way as it has been for sine, cosine, secant, and cosecant. And that is dependent on this k. So if k is greater than 0, we're going to be shifting up. If k is less than 0, then we're going to be shifting down. And the horizontal translation, don't have to worry about.